Learning objectives are, we already mentioned antiderivatives briefly in the last video, so I will do a little more formal definition. And then we discussed the indefinite integrals that follows the substitution and trying different substitutions. So what is the antiderivative? Well, a function capital F is said to be antiderivative of little f if the derivative of capital F is little f, right? So it's the sort of opposite of taking the derivative. Let's do some examples. Let's find the antiderivative of the following functions. So in A we have 2x. So what we are looking for? We are looking for some capital F such that its derivative gives me little f, which is 2x, right? So a little thought might give us x squared, right? From power of derivative, we know that the derivative of x squared is 2 times x, so that gives us 2x. Hence, the antiderivative of 2x is capital F. Okay, let's do B. So I'm looking for, let's say, capital G of x such that the G prime is equal to little g, which is cosine of x. So what I'm thinking is a function whose derivatives gives me cosine of x, right? I'm not taking the derivative of cosine x, I'm trying to find antiderivative of cosine x. Again, from our previous lectures, we know that g of x would be sine of x, right? Because if I take the derivative of sine of x, I will get cosine of x. How about C? So I'm looking for a capital H such that its derivative is going to give me 1 over x plus 2e to the 2x. Well, I can think of 1 over x and 2e to the 2x as two separate functions. So I can try to find the antiderivative of each separately, right? So what would be the antiderivative of 1 over x? Well, we know that ln x satisfies as an antiderivative, right? And for 2 times e to the x, we know that e to the 2x, if you take the derivative, will give 2 times e to the x. So we simply add, right? A interesting question is, if the antiderivative is unique. It's not necessarily. For example, here I could add 5, right? Then if you take the derivative of x squared plus 5, it would also give me 2x. So which means x squared plus 5 is also antiderivative. Or for sine of x, I could, for example, subtract 10, right? So then sine of x minus 10. If you take the derivative, this minus 10 is not important because it's a constant, derivative is 0. And similarly here, I mean, in fact, I could do any constant. And that's the content of the next slide. The theorem tells us the following. If capital F happens to be antiderivative of a little f, then in fact, capital F plus any constant is also an antiderivative. And in fact, this is the most general form of antiderivative, right? So if you take the derivative, we'll get simply f prime, which is little f. And this is the most general form. There are no other antiderivatives. Okay, let's do example. I want to find one antiderivative of this 3x squared such that the antiderivative satisfies this initial condition. Well, what do we know? I can take f of x to be x cubed, right? X cubed, because the derivative of x cubed is 3x squared. However, when I plug in x equal to 1, what do I get? Capital F of 1, 1 cube. Well, it's not negative 1, right? It's not negative 1. So which means this capital F of x equal to x cubed is not the correct antiderivative I'm looking for, because it doesn't satisfy capital F of 1 is equal to -1, right? So this is wrong. So what we do? Well, we say, okay, let's look at the most general form, right? Then this is x cubed plus constant c is an antiderivative of 3x squared. Now we try to find for which c we have this initial condition satisfied. So again, what does that mean? It means if x is 1, then f1 is -1. Well, you substitute x equal to 1, you get f of 1 is equal to 1 cube plus the constant must be -1. So from here you see that my constant must be -2, right? Hence, the answer is f of x is equal to x cubed minus 2, and that satisfies both conditions. The following table gives us antiderivatives of some important functions. So here the k is any non-zero constant. So the first one, for example, is now a power rule for antiderivative, right? So the antiderivative of xn is xn plus 1 divided by n plus 1. You remember the power rule for differentiation, where which was n times xn minus 1. So you subtract, you decrease the exponent. Here you are increasing the exponent, right? Etc. So you can try to prove these statements, and proving is not so hard. All you have to do is, for example, if you want to show secant integers of secant square kx is equal to 1 over k tangent kx plus c, all you have to do is just take the derivative of this, apply the derivative rules, and show that it's equal to secant square kx. Okay, and so on and so forth. I think it's a good exercise to try. So what is an indefinite integral? Well, indefinite integral is nothing but uh, an integral way of representing all the antiderivatives, right? For example, if you capital F prime is equal to little f, in other words, if capital F is the antiderivative of f, then what was the antiderivatives? All possible antiderivative would be f of x plus c, right? So here, this is my integral form of writing the antiderivatives. Okay, so indefinite integral is nothing but the antiderivative. That's how you should think of it. And in fact, bear in mind that the capital F of x plus c, this is a function, right? It's like a function or set of functions. So hence the indefinite integral, when you evaluate indefinite integral, you should expect a function plus a constant. You do not expect a number, right? All right, so let's do some examples. I want to evaluate indefinite integral x squared minus 2x plus 5. Well, what is the antiderivative of x squared? And antiderivative of x squared is x cubed over 3, right? What is the antiderivative of 2x? It's x squared, and I have negative sign in front, so I put in negative here, using sort of linearity. Well, what is the antiderivative of a constant 5? Well, it's just 5x, right? Because you take the derivative of 5x, you get 5. Now, you might think, okay, maybe for each one we need to add some constant, right? Like x cubed over 3 plus c minus x squared plus c, 5x plus another c, and so on. So it's not so convenient to write constant 3 times. So instead, we only place just one constant. So in the previous lectures, we discussed definite integral, right? So what was the definite integral? Well, definite integral was an integral of the form f of x dx, an integral from a to b. And once you evaluate, you get a number, right? However, for the definite integral, we do not evaluate from a to b, right? So what is it? This is something like f of x plus c. So what we have is here the result is not a number anymore. This is, if you like, it's a set of functions, or you can say it's a function plus a constant, right? Antiderivative plus a constant. So that's sort of this is the difference. And how do we sort of connect? Well, the FTC, the fundamental theorem of calculus, makes this connection, right? We already have the connection. So what was the connection? Well, if capital F is the antiderivative of a little f, then the fundamental theorem calculus tells us that integral from a to b of f of x dx is nothing but capital F b minus capital F of a, right? Well, so now you can also observe it from right. So if I evaluate my integral, right? If I evaluate my integral here, my indefinite integral, if I make it a definite integral, which would mean that I need to evaluate my capital F of x plus c from a to b, right? So what happens if you evaluate? Well, you substitute x equal to b, you'll get capital F of b plus a constant, and then we have the minus of capital F of a minus the c, and we see that this c's can cancel, so indeed I get the same quantity, right? So that's sort of the relation between indefinite and the definite integrals. Substitution. As I mentioned in the beginning, substitution technique is by far the most important integration technique. Lots of formulas relating the integral are essentially found using substitution. So we need to really know what it is and how to properly, correctly apply it, right? And as the title suggests, this is nothing but backward chain rule, right? So going backward direction in the chain rule. Well, what was the chain rule? Let's say that my capital F is equal to little f, right? So capital F is in the derivative. Then, if you differentiate capital F, let's say that I have a capital F of u, right? So u is a function of x. So if I differentiate capital F with respect to x, the chain rule tells me that this is f prime of u times u prime, right? Du dx, right? So the derivative of f of u with respect to dx is this f prime u times du dx. In other words, this right-hand side is the derivative of capital F of u, which means the capital F of u is the sort of antiderivative, right? So in other words, if I were to integrate f prime of u du dx, right, this term with respect to dx, I should be getting f of u, right? But wait a second, I can also derive f of u from little f or f prime, right? From f prime of u du, right? This is coming from fundamental theorem of calculus, right? So that's it. So I can denote this du dx by u prime, right? If I denote it by u prime here, so if you do to u prime, then that's it. So this is the content of the substitution method. If you're trying to integrate some sort of a complicated function, you can make some substitution, right? Doing some substitution, it basically boils down to integrating a much simpler function. Okay, so to summarize, here's the situation. So remember, this capital F prime is little f, right? So here you could replace this capital F's by little f, right? So you would get here and here, you would get f of u f of u. Okay, so now let's say that you have some complicated functions, something like this. Then what you can do is, so that the substitution rule tells us that if I make this substitution u equal to g of x, then this sort of complicated integral on the left becomes a much simpler integral f of u du, right? So let's do examples, because it's best explained by examples. All right, let's try to find the indefinite integral of the following expression. So one approach is the following. You can apply the binomial formula to expand x cubed plus x to the 5. What do you get? You will get a polynomial of degree 15. And then you multiply it by 3x squared plus 1. You will get a polynomial of degree 17, right? And then you can sort of apply the power rule for integration, right? So integrate each one separately, sum them up, and plus a constant. But as you appreciate, that's much complicated, right? So here is an easy way using substitution. We also call it U substitution. So U substitution. Well, what can we do? We can, for example, take this x cubed plus x to be my u. Let's try it. Let's try it. Then let's take the derivative of this expression, both sides, with respect to dx. So you will get du dx is equal to, here is going to be 3x squared plus 1. Well, we are lucky, right? So this part is exactly du dx, right? Okay, so let's make this substitution. Then what we get? We get here, instead of x cubed plus x, I have u, and I have power 5 times, and then the second term becomes simply du dx, and times dx right here, right? And what we saw in the previous slide was that in some senses dx sort of cancels, right? Cancels, and you will get u5 du. So it's just the integral of u to the 5. Well, what is the integral of u to the 5? So what is the antiderivative of u to the 5? It's the power rule for integration, right? So it's u to the 5 plus 1, so it's 6 divided by 6, right? Why? If you take the derivative of this expression, you will get u5 plus a constant, because this is indefinite integral. Are we done? No, because the original example is asking integral with respect to dx, which means I need to write an expression in terms of x. What I have an expression of u. So now what we do is we recall what was the u, right? So u is x cubed plus x. Hence we have x cubed plus x. So this is my u, and then I raise to the power 6. Here I divide by 6 plus c. So this is the solution. Another example, integration of square root of 2x plus 1. Well, what can we do? We can do u is equal to 2x plus 1, right? Then du dx is going to be 2, right? That's it. Usually, instead of writing like du dx is equal to 2, we usually write something like this: du is equal to 2 dx. We sort of forget about the sort of the denominator in some sense. Okay, so this is sort of a better way of writing, because that makes lots of things sort of easy to implement. Okay, so for implementation, this is better way of writing. So then let's see what happens. Well, I have this expression right here. So integral, what is this expression? Well, the inside square root is 2 u, right? U. So this is square root of u. And then I say, what is dx? Well, from here you solve for dx. So dx is 1 over 2 times du, right? So we do here multiply by 1 over 2 du. All right. Well, I can pull out half, and the square root of u, I can write it as u to the 1/2 du. Again, I apply the power rule for integration. So I increase the degree by 1, and then divide by this increased exponent and add constant. So what do I get? I get 1 over 2. Here I get u 3 over 2 divided by 3 over 2, right? Plus constant. And then you recall that u is equal to 2x, right? So you make a sort of back substitution. So this is going to give me, well, 3 over 2 becomes 2 over 3 when you take the reciprocal. So the 2's cancel. You'll get 1 over 3, right? So you get 1 over 3, and u is 2x plus 1. So this is 2x plus 1 to the power 3 by 2 plus a constant. So summarizing, here's what we have. You want to integrate f g of x, f of g of x, g prime of x, right? So there is a composition. So that's why we call it sort of related to chain rule. Anyway, what we do is we set u is equal to g of x. Then, as a shorthand, we write du, which is du dx dx. So dx is cancelled. So du is equal to g prime x dx, right? If you take this sort of derivative for both sides, it's du is g prime x dx. And making this substitution, you'll get the integral of f of u du. So what next? Next, you simply integrate this simpler function with respect to u, right? And then you make this back substitution, right? You recall that u is equal to g of x, right? You need to write everything in terms of x again. So let's do more examples. Well, I want to integrate secant square 5x plus 1 times 5 dx. What can we do? Well, you say that let's make u is equal to 5x plus 1. Then du becomes 5 dx, right? So with this substitution, my integral becomes secant square u, and the 5 instead of 5 dx, I have u, right? So this is simply times du. Well, now, what was the integers of secant square? Well, we know that derivative of tangent is secant square, hence tangent becomes the interderivative of secant square, and plus a constant, and we do this last step. Sometimes we miss this, but let's not miss it. So we make this back substitution. That remember that u is equal to 5x plus 5x plus 1, so we get tangent 5x plus 1 plus a constant. Right. So integral of x times square root of 2x plus 1 dx. Well, this looks a bit complicated. Well, still, let's try u substitution. As before, we can say u is equal to 2x plus 1. Then du becomes 2 times dx, right? So from here, we solve that dx. So from here, dx is 1 over 2 du. So then, what do we get here? Well, let's leave x for now. But here, the expression inside the square root, we know that this is square root of u. And instead of dx, I can write 1 over 2 times du. Well, now I have a mixture of x and u. That's not good, right? So I want to have an integral u alone, and then I can go ahead with integration, right? If there are some x variables left, that's not good. So I have to do something here. What is it? What is this something? Well, what do we have? We have u is equal to 2x plus 1. So this original substitution will help me to get rid of x, or replace x by some expression of u. Well, you simply solve for x. What is x here? X here is u minus 1 divided by 2, right? Hence, my integral here becomes, replacing x by this u minus 1 over 2, and let's write the square root as u to the power 1/2 times 1 over 2 du. Great. Well, 1 over 2, 1 over 2, 1 over 4, I can take it out. Then I have this u minus 1 times u to the 1/2 du. Okay, let's expand. I can do this integral of u to the 3/2 minus u to the 1/2 du. Well, now that I have sort of essentially two separate integrals, right? So I can find the interderivative of each separately. Well, 1 over 4 times, what is the interderivative of u to the 3/2? Well, you increase the degree by 1, which will give me 5 over 2, and then I divide by 5 over 2, minus u to the 1/2. Well, this becomes u to the 3/2. We already did it. Divide by 3/2. Right? Everything is multiplied by 1 over 4, and then we have a constant. But then we recall that u is equal to x plus 1, so at the end we get something like this. So here I can write this as 2 over 5 times u is 2x plus 1 to the power 5 over 2 minus 3 over 2 becomes 2 over 3 times 2x plus 1 to the power 3 over 2. Everything multiplied by 1 over 4, and I have a constant. All right, an example involving trigonometric function, namely sine square, right? So I want to find the integral. In other words, I want to find the interderivative of sine square x. All right, what could be the interderivative? Interesting question. Looks like a difficult one, right? Somewhat tricky. So what you can do is you can try to use some of the trigonometric formulas to make it into different form. So what do I mean by this? So here is one trick. The trick is to use the double angle formula, or if you like, half angle formula, whatever you call. So sine square x is nothing but 1 minus cosine 2x divided by 2. So this is one of the trigonometric formulas. Okay, let's see how it helps. Well, I get 1 minus cosine 2x dx, and I can take this half outside of integration. Right, what next? Well, I know how to integrate 1, but how do we integrate cosine 2x? Well, we say that to this end, I can let u equal to 2x, then I get du is equal to 2 times dx, so dx becomes 1 over 2 du, and if you make this substitution, for the first one, you don't have to make this substitution. Basically, you can write something like 1 over 2 times, what is the integral of 1? It's x, right? X. And then I can write the second integral as cosine 2x dx, and then I can go ahead with my substitution. So here I have an integral of cosine of u, and dx is replaced by 1 over 2 du, right? So 1 over 2 du, so I can take out 1/2, it becomes 1 over 4 here, right? Great. So what do we have? X minus 2 minus 1 over 4. What is the interderivative of cosine of u? We know that it's nothing but sine of u plus a constant, and then you remember that u is equal to 2x, so we will get x over 2 minus 1 over 4 sine of 2x plus a constant. So that's the antiderivative of sine square. Well, how do we check it? Simply go ahead and take the derivative of the last expression, and see if you get sine square x. All right, let's try another trigonometric function, namely tangent x. What we know is the derivative of tangent x is secant square, but we do not know the interderivative of tangent x. That's what we are looking for, it, right? Okay, so let's try the substitution. How do we do the substitution? Well, as in the previous slide, we can do some properties of trigonometric functions. Well, it looks like we don't have much chance, right? But try something like sine x over cosine of x dx, right? Okay, so I sort of make the integral look more complicated, but here how it's going to help. I let u is equal to cosine of x. Then du is, what is the derivative of cosine x? Minus sine of x dx, right? Well, look what's happening. So I already have this sine x dx part, right? So this part is already exists. So hence, sort of sine x dx is what? It's negative du, right? Perfect. So then what do we get here? So instead of sine x dx, I replace by minus du. So here is minus du. And cosine x is u, right? Or if you wish, I can take out minus, so it becomes 1 over u du. Well, we know that the antiderivative of 1 over u is ln of u. But you have to be careful. I don't know the sign of u, so I take the absolute value. This is something we also covered in previous lectures, plus a constant. So whenever you take the integral of 1 over u, you need to remember that it's not just ln. It's the ln, then absolute value, right, of absolute value of u. Great, but u is cos x, right? So this is minus ln absolute value of cos x plus constant. Okay, let's do more. So I want to integrate 1 over ex plus e to the minus x. What substitution could help me? You can try different substitution. For example, you can do u is equal to ex, or you can do u is equal to e to the minus x, or you can do u is equal to ex plus e to the minus x, right? So you can try these three, and one of them or all of them could work, right? But here's what I will do. I will put it in slightly different form, and then we will sort of see what's happening here. So what do I do? Well, I can write it as ex plus, I can flip e to the minus x as 1 over ex, right? And then, bring the denominator into common denominator. So you will get ex times ex, so it becomes e to the 2x plus 1 divided by ex, which gives me e to the x divided by e to the 2x plus 1 and the integral of this expression. Okay, so what do we do now? Again, you can try different substitution. For example, you can say u is equal to e to the 2x plus 1, or you can try u is equal to e to the x. So let me try that, the latter. So let's say u is equal to e to the x. Then what is du? Well, du is, what is the derivative of ex? It's ex, so it's ex dx, right? Great. Now, I already have ex times dx at the top, so that becomes simply du, right? And at the bottom, what is e to the 2x? Well, e to the 2x, you can write it as ex squared. And I know that ex is u, right? So this becomes simply u squared plus 1. Well, what is the antiderivative of 1 over u squared plus 1? Well, luckily we know what it is. It's arc tangent of u, right? And we add a constant. Then we remember that u is equal to e to the x. So the answer is arc tangent e to the x plus a constant. All right, so following table presents some of the indefinite integrals. We already did the first one, right? So you can try the others. So the this integral cotangent is sort of similar, but integral of this secant and cosecant, you have to do like multiply by some term, divide by some term, so there's some trick. I think these are nice exercises, so I will leave it as an exercise. All right. The last integral that I want to consider in this lecture is this complicated one, so 2z dz divided by cube root of z squared plus 1. Okay, again, you can try different substitutions, and if you're lucky, you can get it in the first trial, or sometimes any trial could work. Any sort of meaningful trial could work if you're really lucky enough. But anyway, so let's try it. Let's try it. So the first way, let me try something like u is equal to z squared plus 1. Then what is my du? Du is 2z dz. Well, it looks like I'm on the correct direction, right? Because this 2z dz is already appearing on the top. So then, once we make the substitution, at the top I will get du, at the bottom I'll get cube root of u here, and I can rewrite it as u to the minus 1 over 3 du, and simply apply the power rule for antiderivative. So you increase the degree by 1, and then divide by the same degree that you got at constant. So what is this? This is u to the 2 over 3. Here we get 3 over 2 plus the constant, and you remember that u is equal to z squared plus 1, so this is 3 over 2 z squared plus 1 to the power 2 over 3 plus a constant. So we were sort of lucky with our trial, right? Now in the next slide I want to do the same example but with different substitution, and you will see that it will also work. But be careful, it doesn't mean that any substitution works all the time. It's just for this particular example, we are lucky that two different methods works. So the second way is follows. We say u is equal to now cube root of z squared plus 1. Okay, and then what I do is you take the derivative of both sides, right? Du is equal to, but this expression, cube root expression, seems a bit complicated. So instead of doing this, I will do a slight change. But however, you don't have to do this change. I mean, it will work if you just go ahead from here and take the derivative. I think again, try it as an exercise. But from here, I can take the cube of both sides, right? Then I'll get u cube is equal to z squared plus 1. Now let's take the derivative of both sides with respect to x, right? So what do you get? You'll get 3u squared du on the sorry, not with x, with respect to z. So on the right, you'll get 2 times z dz. Well, again, I got this top, right? So then my integral becomes so instead of 2z dz, I now need to replace it by 3u squared, right? 3u squared du, and at the bottom it's simply u, right? So it's much simpler, looks like simpler. Okay, what is this? Well, this is 3 times the integral of u du. Again, we know how to integrate it, so this is 3 u squared over 2 plus a constant, so 3 over 2. Instead of u, I replace this expression right here, so it becomes z squared plus 1. You square it, take the cube root, is divided by 3 plus a constant. And if you compare with the previous slide, we arrive to the same integral.